Yeah, so continue with our work on performance measure. We have a few questions here. And this question is saying machine A has a clock cycle, a clock, sorry, not a clock cycle, a clock of 1 nanosecond period and a CPI of 2.0, clock cycle per instruction of 2.0 for a program X. Machine B has a clock of 2 nanoseconds and a CPI of 1.2 for a program X. So it seems they are running the same program. Now, how much faster, which is faster, and by how much? Now, what you realize is that they are running the same program, right? And if they are running the same program, the idea of the number of instructions they are running is the same, right? So you can choose any value for them, right? So here the question tries to just use n to represent the number of instructions because hey, after all, they're running the same program, right? Now, in calculating the time for A, you realize that there is this formula. Time is equal to what? The instructions per programs times the cycles per instructions times the seconds per cycle. Now, if you take notes, you realize that um, the this is like a chain rule something. So some will actually cancel out, and you realize that you can't then get seconds per program, right? So it's a simple way to memorize the formula actually. Now, when you take A, right, and you go through the process, the instructions per program, we are saying they are running the same program, but they never give us the number of instructions per program. So we are using n to represent it, and that's the n you see. Then we have uh, the CPI, right? The clock cycle per instruction. They gave it explicitly in the question as 2.0 for A, and that's what you see. And the third one is the seconds per cycle, right? So when they tell you clock, it means the seconds per cycle. So and that's what you see, it's one, right? Now when you multiply them, you get 2 times n. Then you can do the same thing for B. So n times 1.2 times 2, right? And you get 2.4 n. Now you have to compare, see which one is faster and be able to state it right clearly, right? Like I always say, just put the bigger number on top so that it will make your explanation easier. And I realized that they are running the same program. However, other features of their machines are different. Now, at the end of the day, B took 2.4 n nanoseconds to complete, whereas A took 2n nanoseconds to complete. Right? B took a longer time, which means that B is not a very good computer. Right? That's just from even looking at it. But the reason I'm asking you to put the bigger one on top is so that you can make the percentage justification simpler. So when you take the ratio of 2.4 over 2, right, that's how you compare. When you have to compare the two things, you just find the ratio. So the ratio of 2.4 n over 2n will give you 1.2, right? Now always remember the base ratio we are looking for is 1, right? So if you have 1.2, that means that we have a zero point 0.2 increment, and a zero point 0.2 increment is what? 20%, right? So that's what you see. Now, which machine has the shorter time? It was A, right? So which means that A is 20% faster than B, right? That's as simple as that. Now, you can go ahead and have another question. So for the exact same thing you saw, this time you are being asked a similar thing, but instead of being given everything and being asked to find the performance. They are trying to see, hey, if the performances are the same, then what are you supposed to get for the CPI of A, right? So they are saying, hey, keep the clock of A still at 1 nanoseconds and the clock of B at 2 nanoseconds. So don't change their clock, right? Now, if we want equal performance and the CPI of B is at 1.2, then what is the CPI of A? So it's the same thing. So you take the ratio time of B over time of A, right? It's equal to. Now, you remember that the time of B, right, will be given by the number of instructions per program, seconds per instruction, and the seconds per cycle. With that in mind, you can effectively calculate the performance, right? So time of B just becomes n times 2 times 1.2, and the time of A is given as what? N times 1 times the CP of A. We don't know the CP of A, but we know that at the end of the day, the performance are equal, so the ratio of the times is 1, right? Now, this will end up in a just simple equation, right? When you solve, you end up with the CP of A as what? 2.4. Not very much of maths here. Okay, there is a third example, and here I think it's solvable with the same methodology. And now we move on to another design law, right, which is called the Amdahl's law, right? So Amdahl's law is a bit of saying, hey, you have a system, right? Now you can be a very good engineer. Some way, somehow, you are able to tweak part of the system and make that part of the system faster. But how does it compare to the whole system? So, for example, you have a very nice processor, right? And you happen to be able to tweak it some way, somehow, so that you speed up multiplication operations by 2, right? Now remember, it only affects multiplication operations. It will not affect addition or subtraction, right? So when you are given a set of instructions, then how would this increment in multiplication affect the whole system, right? We know that fine, you've increased only the multiplication by 2. How does it affect the whole system? That's what the Amdahl's law is trying to clarify, right? So Amdahl's law gives speed up, right? And speed up is given by this expression, right? So you have performance for using entire performance for entire task using the enhancements over performance for entire task without using the enhancements. Now, if you're interested in getting the formula of it, it's simple. You realize that when we talk of speed up, we usually want to think of a very positive factor, right? And now we know that the performance for the entire task with the enhancement will be greater than that without the enhancement, right? Yes, so you put it on top. Now, when you have to think about this in terms of times, remember performance is inversely proportional to time. So it means that the execution time without the enhancements will now be on top. The execution time for the entire task with the enhancements will now be at the bottom. Or if you want to think it about another way, you realize that the execution time, we want a positive factor for the speed up, a large number for the speed up. So you realize that we'll put the execution time without the enhancement, which will be bigger than the execution time with the enhancements, right? So that's just a way to get the formula in your head. It's not any new thing. Yes, so let's try a calculation, and this is actually a derivation for the Amdahl's law, right? So we don't have to really go through the whole thing, but it's a bit simple when you take a look at it this way. It's saying that, hey, listen, no matter how good an engineer you are, right? If you only enhance part of a machine, right, there will be some parts which, because they have not been enhanced, they will not change, right? And those parts are represented by the 1 minus f. Now the parts which you have enhanced, right, their time will decrease by a factor of 4, right? Yes, and when you multiply this by the total time, you get the total execution time with enhancements, right? Now you can make change of subjects and get the speed up ratio as you wish. So just the change of subjects matter. Now this becomes at the end of the day the formula for the and for the speed up, right? So after you've enhanced only parts, so the part you've enhanced is called the F. That's what you see. After you've enhanced only part of a machine, right? Then it means that the speed up will be given as 1 over 1 minus F plus F over S, right? Where the 1 minus F represents the part which never got speed up, and the F over S represents the part which got speed up over the factor of the speed up, right? So the S is actually the factor, the number of times that is sped up. We'll see that in an example, so don't worry. So this is a practical diagram, right? It is saying that, hey, your total time, right, if it is normalized as a fraction, right? A total fraction is 1, right? It's a total fraction is 1. So if the total time is normalized as a fraction, then we can say, oh, you take 1 unit to execute your whole program. However, if by some way somehow you're able to optimize part of your program, right? Then it means that there'll be part of your program which you never optimized, right? So let's assume that the part you optimize is called f, and the part you never optimize is what one is called takes a time f, and the part you never optimize takes a time what 1 minus f, right? Now the part you optimize f will not still take the time f, because you've optimized it, but it will be decreased by a factor. And what is that factor? That factor is S. And that's what you can see here, right? So no matter how good you are, if you optimize only part of a system, only part to be optimized, there will be some parts unoptimized in the equation. And that mixture is what the Amdahl law seeks to take care of, right? So that's what you see. Now let's see a quick example on the Amdahl's law so that we will be clear with it. So the question is simple. It says you have a race machine, right? And you have the following instruction mix. So as you can see, you have this table like this. I think the diagram should have made it clear, but I have a table like this, right? And you have it being showing all the various instructions supported on a race machine. You support ALU, you support load, you support store, you support branch instructions. However, there is a catch. Um, 50% of the instructions are ALU instructions. Right? And these ALU instructions take 1 cycle to complete. They have a CPU I of what? 0.5, right? And whenever they occur, right, each ALU instruction takes like in the total operation of the machine, 23% of the time it is doing ALU instructions, right? Now you can go ahead to the other instructions and they have their ratios and respective distributions. But the real question is here. So it says if a CPU design enhancement improves the CPI of load instruction from what 5 to 2. Remember, CPI stands for clock cycle per instruction, right? Clock cycle per instruction. Now, the smaller the value of the CPI, the better, right? Now, somehow we've been able to reduce the CPI from 5 CPIs to 2 CPIs, right? And it says, what is the resulting performance of this enhancement? Well, when you see a question like this, just take note of the parameters. So we'll just take note of the first parameter. First, which fraction has been enhanced? The question talked about load instruction, right? Now remember, in the dealing of performance, our main entity is time, right? So take a look at the time. So realize that load instruction takes 45% of the time. It means that in the whole working of the machine, 45% of the time it is doing load, right? And that can give you an idea of the performance. So 45% of the time, 45% is the same as 0.45 as you see here. Now, we realize that fine, 45% of the time we are doing load instruction. So we are thinking that, oh, this time taken by that 45% will reduce. But we know that the remaining 55% or some ways will not reduce because nothing about them has improved, right? So we'll take note of that 55%. The 55% is the same as what? 0.55, right? So the affected fraction is 45, which is the same as 0.45. Unaffected is what? 1 minus um, 0.45 or 100 minus 0.45%. I mean, this is just percentages and fractions conversion. Now, we are come to look about the factor of enhancement, right? Now, it's a bit of long talk, right? But do you remember that performance is inversely proportional to execution time? And execution time is also directly proportional to the CPI, which means that performance is inversely proportional to the CPI, right? So it means that the new performance over the original performance will be equal to the old CPI over the new CPI, right? Or if you can't get it over, just remember that because they said it's an improvement from 5 to 2, that means you have to get a number greater than 1, right? So 5 over 2 will give you, but 2 over 5 will give you 0.4, which is wrong. right? So that's what you see. But the ideology is there. Performance is inversely proportional to execution time, but execution time is directly proportional to CPI, right? And you can know that then in the end of the day, if you are finding the factor S, right, it will be what the old CPI over the new CPI. Now we have almost all of our parameters. We have our F, we also have our S. So we can use the Amdahl's law. And when we use the Amdahl's law, we get what 1 over 1 minus F plus F over S. You substitute your values and you get this 1.37. Simple as that. What it means is this: you were able to increase load instructions 2.5 times, right? I think this is more than 100%, but let's not worry. So 2.5 times, right? However, in the perspective of the whole machine, right? When the machine is executing a whole program, right, with that kind of distribution of instructions you see there, right? There is only what it's only made faster 1.37 times, or there's only a 37% improvement, right? That's the ideology provided here. That although you have been able to increase the performance drastically for an element, right, in the concept of the whole machine, it may be smaller. And we have a typical example here. Now, there is an alternate solution to that, right? There's an alternate solution to that, and the alternate solution is also based on the same perspective. It says, hey, at the end of the day, right, whether it is the new machine improved or the old machine improved, there are some things you never really changed. For example, you never really change the cycles between the new improvement and the old improvements. The load instruction will take the same number of cycles. Now, the total amount of time for each machine will be viewed as a total of one, right? Um, the frequency of the instruction will also be viewed as almost the same. But what will actually change is the CPI, because we made the improvement in the CPI, right? So why don't we limit our calculations to that point? Now, and limiting our calculations to that point, let's calculate our old CPI. Our old CPI is simple. Sum all of this, because that's the original thing before the improvement. And when you sum all of this, you get 2.2, right? Now, our new CPI. Well, our new CPI is also not much. It's not much of a problem, right? Remember, this CPI, right, was actually gotten from these parts, right? So when you multiply the frequency by the number of cycles, you get the CPI, right? So you realize that 50% times 1 is 0.5, 20% times 5 is what? 1. Yes, and you go on, you get the CPI. Now you realize that the CPI of load instructions was from what? 5 to 2, right? So it means that this time when you are re-evaluating this column, right, instead of using 5 4 here, you use what? 2, right? And that's the only change, right? So now when you use 2 and you start doing the multiplication, 50% times 1, it will give you 0.5, I mean, but 20% times 2 will give you 0. What? 4, right? So instead of here being 1, here will be what? 0.4. Now you can go ahead with the other calculations; they won't change, right? And um, that's that's really that, right? So when you come back to finding the speed up, remember the speed up will be the ratio of the original execution time to the new execution time, right? Remember that relation: performance is inversely proportional to execution time. The execution time is directly proportional to the CPI. Right? And the speed up has to be what? A number greater than 1 if you are really talking about an improvement, right? So once you do that, you realize that at the end of the day, you'll be doing a ratio of 2.2 over what? 1.6. And that will give you 1.37. Now remember, the 2.2 is the old CPI. The new CPI, if you sum 0.5 with 0.4 with 0.3 and the other 0.4, I think you get 1.6, right? And that's what will give you the new CPI. So which is the same as what you got from the original question, right? It's actually the same. Now, one last example before we move on. So it says a program runs in 100 seconds on a machine with multiply operations responsible for 80% of this time, right? By how much must the speed of the machine be improved to make the program 4 times faster? So you are saying, hey, you have a machine, right? And now the machine runs a total of 100 seconds, but the total of 100 seconds is running. 80 seconds is used for multiplication. Now, till we want somehow to improve the 100 seconds running time to just um, to make it 4 times faster, right? So we want to make from 100 seconds, we want to come towards 100 over 4, right? Which is what 25 seconds, as you can see, right? So desired speed up is what the speed up without enhancement. So without enhancement, we are running at 100 seconds. Now with enhancement, we don't know how much we'll run at, right? But we know that what our speed up should be what 4, right? Now you make change of subject, you get a total of 25 seconds, right? Now we go back to the Amdahl's law, or it's just this is actually logical at this point. Remember that our machine now, which was running at a total of 100 seconds, is now coming to run at what 25 seconds, right? According to our new specifications, right? Now remember it's come to run at 25 seconds because we are going to make an improvement on a specific hardware, the multiplying hardware, right? The multiplying operation, right? So it means that the remaining of the operations would have to remain the same, right? So it means that the remaining of the operation will be what 100 minus 80, right? Those are the parts which are not multiplying instruction. Those will be what 20 seconds. Now the multiple operation is going to be spread out by a factor, but we don't know that factor. But we know that it will be the original 80 seconds over some factor s, right? That would give that speed up. Then now you solve the equation. So you can move the 20 seconds here, you subtract to get 5. Then you do change of subject and then really end up with what? 16, right? What it means is that if you want this machine to be able to run 4 times faster, you have to increase multiply instructions 16 times. Now you could have used the Amdahl's law for the same thing. So the Amdahl's law says the speed up will equal to 4, right? And at this time we are looking for s, right? We are not looking for the speed up, we are looking for s. Now we put it inside and we realize that the factor which is not enhanced, right, which we are not enhancing, will be what the remaining 20 seconds or 0.2. The remaining 20 seconds or yes, the remaining 20 seconds, right, or 0.2. So 1 minus 0.8 is 0.2. Then we have to take the 0.8 seconds which we are improving over s, right, and we solve and realize that till you get 16. So when you solve 1 over 0.2 plus 0.8 over s is equal to 4, you solve for s, this equation, you get s is equal to 16. And that's that for the Amdahl's law. Now, in as much as you're observing this, notice that there are some cases where it is impossible to get an enhancement, right? Some of them will give you negative value or zero values, right? This very same question, if we had planned to go for uh, 5, want to make the program 5 times faster, right? Would have gotten 20 here, right? So here will be 20 instead of 25, and here will be 20. I would have gotten what 80, you got 0 here. Now come and get 80 over 0, right? It's just an assumption. And this will mean that there is no improvement we can do to the multiply instruction to make this program, this same question 5 times faster, right? So just take note of that. And things like that do happen. And yeah, I think it's the same question.